Hi, everyone. We've set up this Being an Engineer podcast as an industry knowledge repository, if you will. We hope it'll be a tool where engineers can learn about and connect with other companies, technologies, people, resources, and opportunities. So make some connections and enjoy the show.
Well, our greatest moment of publicity, our 15 minutes of fame, so to speak, was the chief surgeon was interviewed on Good Morning America, and he came in and he had our models in his lap.
Hello, everyone. Welcome to the Being an Engineer podcast. We are co-host Rafael Destai. Today we have another very special guest, Crispin Weinberg, who is an anatomical engineer and entrepreneur, the president of Biomedical Modeling Inc., which produces 3D printed patient-specific models for surgeons and providing anatomical engineering services for medical device designers. He was previously a chief scientific officer of Angio-Oncology Sciences Inc., co-founder of Organogenesis Inc.
Organogenesis.
I really appreciate the correction. Thank you.
Yes.
And research fellow at MIT, PhD in Neurobiology, Harvard University Physics, and SB Mathematics from the University of Chicago. So, Crispin, welcome to the show.
Well, thank you, Rafael. I'm delighted to be here. I think it's a fascinating podcast, and I look forward to an enjoyable conversation with you.
I appreciate it. Is there anything else that I may have? I actually like when people correct me so I can improve. Anything else I may have mispronounced in the introduction?
I'm not sure. You may have stumbled a little bit over anatomical engineer the first time. So also
Perfect.
Like to make that clear that it's anatomical.
Let's start there because you are the first anatomical engineer that we have in the podcast. Could you define for us what is an anatomical engineer?
Oh, great. Well, probably the first because I actually coined the term to try to describe what I do concisely. So an anatomical engineer works primarily with medical imaging data and producing 3D models of it. We produce both physical models using 3D printing technologies and virtual models, which can be a variety of formats from mesh models, which are more for visualization, to CAD models that you can use for simulation and even things like CFD analysis. So
I saw on your website, I found you by looking up on Google 3D CAD biology and 3D CAD organs. And that's how I came across your company, Biomedical Modeling Inc. So tell us about Biomedical Modeling Inc. in very simple terms. What are the services you provide and who are your customers?
Oh, great. Yeah. So we provide several different types of services. First, and the way we started was to take medical imaging data, primarily CT scans or CAT scans, and produce 3D printed models for surgical planning, prefabricating prosthetics, and training. You might wonder a little bit, why do you need to do this? The surgeons often have a great deal of experience looking at medical imaging data. And but still, the way I put it is, we, that is people, have spent millions of years evolving to look at three-dimensional objects and understand what they're looking at. We've only spent the last 500 years evolving to look at two-dimensional representations of three-dimensional objects and understand them. So we're not very good at it yet. Give us another number of thousands or hundreds of thousands of years and we won't need these models. So that's one aspect of models for surgeons. A second aspect is CAD models, primarily for medical device designers. Now, probably most of our audience is familiar with CAD software and how it works. It
Correct.
works on geometrical objects, so circles and lines and ellipses. Organic three-dimensional shapes do not fit very naturally into CAD. If you try to import a mesh file into your CAD program, it wants to treat every single polygon, triangle or quadrilateral, depending on your mesh, as a single face. And so you immediately have this structure which has hundreds of thousands or millions of faces and is totally unworkable. So how do you get organic shapes into CAD? And basically, we go through that process, taking the mesh file, putting NURBS curves on it, exporting it as a step file, and importing it into a CAD program, often with lots of back and forth to correct problems because it's easy to get self-intersecting faces or other sorts of abnormalities. So you need to do that. And you also need to do that taking into account a little bit of what the final use is. So what you do for somebody doing a simulation might be very different than what you do for somebody doing a CFD study where they're interested in the flow in one direction. So it's not just a simple press a button, but there's a bit of art and experience to it as well. And so these are very useful for medical device designers who want to test, their device on anatomical structures, on human anatomy before they put it into people.
See, let's talk about the process of editing the mesh file for a little bit, because myself and a lot of our audience here, we're very familiar with CAD and a lot of them with SolidWorks. So once you take the CT scan, what would be the next step? How do you work the file?
Okay, well, to get the CT scan, just to refresh people's memory, is essentially a three-dimensional X-ray, and it's usually exported as a series of images that are like slices, very much like you would slice a file for 3D printing. And what you want to do on that is analyze the data to put it together as a three-dimensional model. So we primarily look at the density of the CT scan. The density of the CT scan, because it's X-rays, reflects the density, the atomic numbers, actually, of the tissue that you're looking at. So bone will appear white because it's got a very high X-ray density. Calcium has a high atomic number. And air appears black because it's got a very low density. And most soft tissues appear various shades of gray. So we make essentially masks very much like you would do in Photoshop based on density and stack them together to make a three-dimensional object. Then editing involves cleaning that up, because if you try to pick all the regions of a certain density, if you're looking at a very clear object like a bone compared to soft tissue, it will probably do it fairly well. But when you start getting into more subtle objects, but in the soft tissue range or some of the thinner bones, you end up getting places where you have to sort of manually go through and remove parts you don't want connected or fill in little holes. Also, if you have metal objects, of course, they have very high atomic numbers, so they'll produce artifacts, and you'll see that as streaking and black areas, and so you have to edit around those. So there's a fair amount of understanding what you're looking at in the CT scan and making sure that your masks reflect that, and then you grow that into a three-dimensional structure, into a mesh. You can export it as a mesh. It is actually in the medical imaging processing program, it's actually a point cloud. And so, but you can export that as a mesh by picking out that density. Usually that mesh is still very, has problems that you need to fix. So the mesh represents the surface as a series, typically of triangles, as an STL file. STL originally stood for standard tessellation language and then sort of got pushed into being called stereolithography language. So there's a kind of ambiguity about what it stands for, but it means that you're representing the surface as this large number of triangles. And a human skull, for example, might have 500,000 to 1 million triangles when you've exported it. So it has a lot. If you just imported those into SolidWorks, a lot of, quote, faces. So it's a fairly complicated structure.
May I ask a question?
Sure, absolutely.
So once the MRI or CT scan is taken, you have data, the slices, and then
Yes.
would the term be curate the data? What's the term?
The term that's actually used is segmentation. We're dividing it into the segments of different density. So that's officially what the term is for describing that process of isolating three-dimensional structures.
The segmentation, in what software do you do it in?
Okay. We do it in a software called Mimics, which is made by a company Materialize in Belgium. That is pretty much the gold standard for segmentation software. There are others around, but mostly, and they'll work fine, but they don't have the same suite of editing tools that allow you to take care of artifacts and edit out artifacts effectively, and trace long, skinny things like nerves, so that essentially it is a tool for drawing essentially a cylindrical spline along a path if you can trace where a nerve runs.
That's actually a very good explanation. Sorry to cut you off. I'm just like every little by little, I'm trying to digest what you're saying. It's very technical, but you're doing a wonderful job explaining it.
It is fairly technical, and it's also fairly visual. So talking about it on a podcast is, that's a little bit of a challenge in a way. So I'm enjoying trying to figure out how to articulate some things that when typically I explain it to people, I actually show them on the screen. Well, here's this area of density, and that's a bone, and this is a tooth, and this is something else. They go through a scan, and people get it very quickly.
But number one, two things.
An interesting point, if I can make a digression.
Okay, go ahead.
One of the values of these models to surgeons and is also explaining to patients what they're going to go through and what's going to happen. A very interesting study was done early on that when the surgeon explained what the procedure was just verbally to a patient, they had the sort of modest understanding of what was going on. When they were shown pictures of the scan and the surgeon said, here's your heart, when we're going to do this, for example, their understanding actually went down because they were just so mystified by what they were looking at on the scan that made their understanding go down. But when a surgeon used a 3D printed model to explain what was going on, their understanding went way up, and they were much happier about the procedure and much more likely to do whatever follow-up is necessary to improve their recovery because they had a much better understanding of what was going on. So they're very effective tools for this sort of patient education as well.
Right on. Well, I want to go back. I first want to get down the process before we get into all the benefits. But unquestionably, having a patient look at what's going to happen or the biology of what the surgery is going to be like, I think it's amazing and could provide a better understanding. But going back to the step of segmentation, using the Mimics software, once you finish that, do you import a mesh file into SolidWorks? Did I get that right?
No, then we go through. Well, you could try to bring it directly in, but when you try to do that, if it has too many triangles, SolidWorks just crashes. The number of triangles you can import actually directly has been steadily going up. When we started doing this sort of work with SolidWorks, I think we started working with it in 2003. You couldn't import very many mesh triangles at all. So number is steadily going up, but it still doesn't really treat it that way. So what we do is we use another process, essentially a reverse engineering software. We use GeoMagic Studio, but there are quite a variety of them around. And basically you take that, you clean up the mesh, various tools sort of smooth it so that the little irregularities don't appear. If you actually export a very detailed mesh, you can see, sort of stair steps for the individual slices of the CT scan. Obviously, the skull doesn't, or whatever structure you're looking at, doesn't really have those stair steps, so you can smooth those out. And you can fill little holes if you don't need all that level of detail, or if they're due to artifact, and sort of smooth out the mesh so it's clean. You eliminate any places where there are self-intersections, which may look fine if you're looking at it just as an object on a screen, but if you try to 3D print it or do CAD analysis on it, you can't do it. So you have to clean it up a bit. And that's done in the reverse engineering software. Then if we're going to 3D print it, we can simply save it as an STL file and send that to a printer. If we're going to do CAD on it, we then try to simplify it by approximating the surface with curves that are laid on the surface, called NURBS curves, or non-uniform B-splines. If you've used Rhino, for example, you're probably familiar with NURBS curves. But they essentially put like lines of latitude and longitude on the surface to approximate the shape of the surface. There's definitely some loss of detail when you do that. And one of the things that we have to work on very closely with our customers is what level of detail they need preserved in a CAD model. Those NURBS curves can then be exported as a step file, and the step file can be imported into SolidWorks. Sometimes it comes in very cleanly. Sometimes it comes in with lots of errors. And if you run import diagnostics in SolidWorks, you get a long, hideous list of problems. And you sort of go back and forth between the reverse engineering software and SolidWorks fixing the problems. Usually if they're relatively small and few, you can fix them in SolidWorks. But if you really have significant problems with the mesh structure, it's generally easier to repair them as a mesh and then import them into SolidWorks. I should also mention that when you've imported such a file into SolidWorks, you end up with something that doesn't have a history tree. It's just a solid, or what we sometimes call a dumb solid, because it has no history. You cannot, and there are no sketches. You can't edit it in any consistent way. You can push and pull on it. You can combine it with other things. For example, if you want to make a model of an artery and put a hose barb on the end so you can plug it into a model circulatory system, you can do that combination in SolidWorks and produce a file that you can then print that you can work with.
Very well explained. I think you mentioned that visuals are needed not needed, but you usually have visuals handy to explain this. But for everyone that's listening to this driving, that was excellent. Thank you. My next question is going to be about something that you touched upon, the level of detail of these files. What determines, of course, the customer will ask you, but in which cases do you need more detail than others?
It really depends on what a customer wants to do with it and is concerned about. So if you're making a model that's going to be used for designing dental work, for example, for orthognathic surgery, you need a fairly high level of detail in the teeth and lower levels in other structures. So you can actually make some regions very well detailed and others less highly detailed. If you're interested in a blood vessels, you may be interested in branches which are larger than a certain diameter, say larger than 1 millimeter diameter. So we could smooth out the very small branches, most of which we probably wouldn't even see on the scan. But if there are any that we do see, we would be able to smooth those out. And then include only the larger ones. So there's really a lot of back and forth with the customers, and I think often I would say the most important criterion for the success of a project is a lot of communication with the customer or client to make sure that we're meeting their needs. Another, of course, restriction on the level of detail is the original data. The typical slices in a CT scan are anywhere from a 0.5 millimeter to 5 millimeters apart, depending on the scan, how large an area it covers. So we cannot improve on the resolution of the original scans. One of the difficulties with MRIs as opposed to CTs is that MRIs tend to have poorer spatial resolution. They do have the advantage of much better soft tissue contrast. So if you're interested in, for example, looking at the difference between fat and muscle, you would almost always want to use an MRI scan, even though the spatial resolution is not as good.
I see. I want to take a real quick break to mention to our listeners that this podcast is sponsored by Pipeline Design and Engineer. And if you visit teampipeline.us, is where you can learn more about how we help medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automation machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. Also, a friendly reminder to our listeners that we really appreciate your podcast reviews. We're trying to get to 100 5-star podcast reviews on the App Store. It really helps other people find the podcast. I'm here with my guest, Crispin Weinberg, and my following question is going to be, you mentioned several softwares are needed to edit the scan file before it's delivered to the customer. So my question is one person usually able to do all the editing, or do you need multiple people on your team with different software skill sets to do this?
One person with a sufficient background and training can certainly do it, but often people will like to specialize in one area or another. So one of the ways I like to describe it is that what I do is probably about 50% engineering and 40% medicine and 10% art. The exact proportions may vary a little bit from one project to another, and certainly do. But there's a mixture of skills. And one of the things that I've often done is when looking for people, when I look at the resumes, I'm usually looking at biomedical engineers, but if they say anything about, doing art projects of any sort or ceramics or, particularly three-dimensional art type things, I tend to look very favorably on those. So that's, a very important criterion for trying to find people who can do this. It involves, a very good sense of 3D visualization, which most engineers have, of course, but also, a sort of artistic sense of trying to make it, because you can make a three-dimensional model, and if you just exported it from the medical imaging processing software and built it directly as that, it would probably look kind of ratty or ugly. But with a little bit of editing, you're not actually changing the data, but you're making it so it comes out looking much nicer. And one of the ways I describe what we do, we make things that are both beautiful and terrifying at the same time. My favorite example, if you look at our website, the biomodel.com, there's a picture of a large tumor in a jaw that we've colored red with the bone transparent. If you hold that up to the light, it's beautiful. It glows like a ruby. It's gorgeous. But at the same time, imagining this fist-sized lump growing on somebody's jaw is really terrifying and frightening and horrible. So it's that sort of fascinating combination of things which are both beautiful and terrifying.
So it sounds like you've been doing this for 20 years. Is that right? Biomedical Modeling Inc. Is that right?
That's right. Yeah, just about 20 years.
Congratulations.
Well, thank you. It's been a pleasure.
I wanted to ask you, you said we, so it doesn't sound like you're a one-man team. How big is your team?
Well, it's actually pretty small. Really, right now, it's just me and one other biomedical engineer and a part-time bookkeeper. So it's gotten pretty small. At times, it's been up to like 4 or 5 people, but it's not a huge business. Partly because I like to keep my hands on a lot of it, and a lot of it is this steady communication with the customers.
I see. Well, I want to ask you some questions about business, just so we can get, if anything's off limits, just please let me know. But I want to get an idea of, like, what's your best seller in terms of what's the CAD file that people tend to ask for the most often?
Well, most people in terms of CAD files are probably looking at parts of the skeleton that is used, I think, a lot in simulating how bodies function and respond to various accidents and devices and repairs. It's also probably makes sense because the skeleton is rigid and unyielding, and making physical models of it is pretty a good representation. So that's probably the area where we've made the most CAD files. The second most is cardiovascular, which is, of course, the complete opposite. It's very soft and moving, but the heart, of course, is very complicated and doing minimally invasive surgery where people are feeding catheters up the leg and into the heart and doing procedures is an area that requires a lot of training and simulation to make sure your device can get around all those curves of those blood vessels and do its job. And so we've made quite a few CAD models for the heart and particularly for minimally invasive mitral valve surgery.
Perfect. What excites you the most about working in Biomedical Modeling Inc?
I think what really excites me is being able to use these engineering skills to make things that help people. It's really wonderful to feel that we've been part of making many of the devices which help improve medical care and make it more human. One of the other areas that it can be very useful for is what's starting to be called more personalized medicine, where you can actually customize devices for the individual patient, and as well as, for example, pharmaceutical treatments being customized for the individual patient. I think we're coming into an era where we recognize that different people have different metabolisms and different bodies and different anatomies, and they react differently to these things. So instead of going to this shelf and buying a hip implant and saying, well, I'm going to put in one that's either small, medium, or large, you find one which fits the patient shape and actually can make it. There are a number of companies involved in doing things like that and starting to make products that are actually customized to the individual patient. And I think we're going to see much more of that in the next decade or two.
Fantastic. If you were an 18-year-old about to enroll in college, it's still you, what major would you choose and why?
Well, I probably would choose biomedical engineering right now, because I think it's just fascinating. I think the way the body works is a marvelous machine. So let's say the way the different parts work together are just fantastic and truly fascinating.
Is it possible, I know we're jumping subjects, but these questions are just popping up in my mind. Is it possible to run FEA analysis on some of the 3D scans you do?
Well, again, you don't do FEA directly on the scan, but you can certainly do it on the CAD models that we've produced from them. And we've certainly made CAD models for companies doing FEA type analysis.
Wonderful. Yeah, I misspoke on the CAD file. That's what I meant. All right. Well, is there something that I haven't asked you that maybe I should have asked you that you want to share with the audience?
Well, I'd love to talk about some of the special cases we've done. Probably the most famous case, it was actually just about 20 years ago now, which is hard to imagine, but there were conjoined twins from Guatemala who were joined at the back of the head, and they were going to be separated by a team at UCLA. They had to be separated because they were joined at the back of the head, and eventually the brains would grow into each other and compress the two brains, and they would die from that, probably somewhere around 4 or 5, if they had managed to survive that long. So we got to make models for planning that surgery, and it was a very interesting experience because when we weren't initially involved in it, and the chief surgeon had a resident who had worked with our models at a previous hospital where he'd been, and he said to the surgeon, "You should get these models." And the surgeon said, "Nah, why do I need that? I can look at the scans. I know what I'm looking at." And fortunately, the resident persisted. He said, "Okay, let's do it. But we're doing this case pro bono. We don't have any funds for it." And so they asked if we would donate our services and make models. And we said, "Well, yeah, this is very exciting and really challenging." So we agreed to donate models. And we made them. We made actually 3 models, which turned out to be very successful. 1 model of each girl's head, and then 1 model of the blood vessels between the brain. Well, the day that the surgeon received the models, he called us up and said, "I saw something on the models that I hadn't seen before in any of the images that I'd looked at." And so, first of all, it already showed that they're very powerful educational tools. And as I had mentioned earlier, we're used to looking at 3-dimensional objects and understanding what we're looking at. When you're looking at the 2-dimensional images, you tend to only look for the things you think you're looking for. And you don't really notice the things that you're not looking for, like the proverbial gorilla in the room sort of thing, that you don't look at those things because you're not looking for them. When you look at the 3-dimensional object, you see, oh, this part is twisted, and their spines were twisted in a way that he did not know. So it probably won't make any difference to the operation, but it's good to know just in case it does. The next thing that we learned, well, our greatest moment of publicity, our 15 minutes of fame, so to speak, as the chief surgeon was interviewed on Good Morning America about this procedure before it took place. And he came in, he had our models in his lap. And he, at one point, picked them up with the 2 heads joined together. We'd put little alignment pins in there. And he pulled them apart, said, "This is what we're going to do." And this described, of course, the models having been made by our company, Biomedical Modeling in Boston. And so this was incredible publicity for us, of course, and very exciting, and probably also the first time many people ever saw or heard of 3D printing, because at that time it was primarily something that was used by aerospace engineers and automotive engineers. And outside those areas, it was not known very widely. So it was also, I think, an important moment in publicity for our industry as well. Now, the whole industry of additive fabrication. Then the next great moment was when the operation took place. It was pretty big news story. And after the operation, which took, I believe it was 28 hours, not everybody being there all the time, obviously. And we'll get to that in a second. Then all the big news media and so on were trying to call a surgeon and interview him about how it went. And he called us to thank us for the models, because he knew that he would probably still be in the operating room, because it would have taken longer if they hadn't had the models for planning. And the result might not have been as successful. The result was quite successful. Both girls survived, one with some neurological defects and one quite normal. Just remarkably good, because they actually shared blood vessels in the brain. So getting back to one of the other things I had mentioned, it was very fortunate we sent the 3 models. We'd only been asked to make models of the bone, the skulls, but it turned out the operation, in addition to having the chief plastic surgeon, also had a chief neurosurgeon who was going to do the dissection of the blood vessels. And so he had this model of the blood vessels, which helped him. And particularly later, we got video footage of the operation, and we saw that the chief neurosurgeon and the chief plastic surgeon, going off, getting together, looking at the models and consulting and talking about what they were going to do, and then going back to the patients. Another use of it, the models, had been for choreographing the operation. As I'd mentioned, the operation went on for a long time. Over the course of the operation, there were probably about 50 different people at one time or another. They were also starting with one patient and ending up with 2 patients. So they essentially had to hold a dress rehearsal of who was going to be where when. And the models were very useful as sort of serving as a surrogate that they could put have together and then pull apart for that. Another use, which was totally unanticipated, was that the anesthesiologist used them to anesthetize somebody. You have to put a tube, a nasogastric tube, down their throat, down up the nose and down into the throat, to make sure they don't aspirate, they don't drown in their own fluid secretions when they're unconscious. And normally you do that by tilting a person's neck back so that you sort of straighten out the throat, and it's much easier to insert the tube. Of course, with the girls who were joined at the back of the head, you couldn't bend their heads back in that way. And so she had to use the models to figure out how she was going to insert the nasogastric tube. Not something anybody had anticipated as a problem, but it turned out that it was solving that problem, or helped solve that problem in advance. So anyhow, that's a fairly long story about it. I could talk on and on about it, but it was an extremely exciting and gratifying thing to be involved in this procedure, and something that was very successful. And we got pictures from their 10th birthday party, which was really delightful. So we were very happy to be part of that.
Fantastic. Well, we're going to have links in the show notes for the articles that you reference here, your 15 minutes of fame, which I thought was pretty funny. And hopefully we can drive some traffic to your website to make people aware of this wonderful resource. Any last words of encouragement for any engineers, maybe still in college?
Well, I would encourage people to learn as much as you can about different fields. You never know how they're going to fit together. I would describe I describe myself now as an anatomical engineer. That didn't exist at all when I was in college, but by learning about physics and biology and mechanics, in a position that I could come to do something and help develop a new field that moves things forward. So I encourage people to learn about many different things, because many of you will be working in careers that don't exist now, but will in the future. And it's very exciting to be part of that, building the future for people. So thank you, Raphael. I think this is great.
Yeah, thank you so much for being on the podcast. I appreciate it.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.